The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today, we're going to continue our discussion of parametric curves. I have to tell you about arc length. And let me remind you where we left off last time. This is parametric curves. Continued. Last time, we talked about the parametric representation for the circle, or one of the parametric representations for the circle, which was this one here. And first, we noted that this does parametrize, as we say, the circle. That satisfies the equation for the circle. And it's traced counterclockwise. The picture looks like this. Here's the circle. And it starts out here at t equals 0, and it gets up to here at time t equals pi over 2. So now I have to talk to you about arc length in this parametric form. And the results should be the same as arc length around the circle ordinarily. And we start out with this basic differential relationship. ds squared is dx squared plus dy squared. And then I'm going to take the square root, divide by dt. So the rate of change with respect to t of s is going to be the square root. Well, maybe I'll write it without dividing. I'll just write it as ds. So this would be dx dt, the quantity squared, plus dy dt, the quantity squared dt. So this is what you get formally from this equation if you take its square root and you divide by dt squared in the, inside the square root, and you multiply by dt outside so that those cancel. And this is the formal connection between the two. We'll be saying just a few more words in a few minutes about how to make that sense of that rigorously. All right, so that's the set of formulas for the infinitesimal, the differential of arc length. And so to figure it out, I have to differentiate x with respect to t. And remember, x is up here. It's defined by a cosine t. So its derivative is minus a sine t. And similarly, dy dt is a cosine t. All right? And so I can plug this in, and I get the arc length element, which is the square root of minus a sine t squared plus a cosine t squared dt, which just becomes the square root of a squared dt, or a dt. Now, I was about to divide by t. Let me do that now. We can also write the rate of change of arc length with respect to t, and that's a in this case. And this gets interpreted as the speed of the particle going around. So not only, let me trade these two guys, not only do we have the direction is counterclockwise, but we also have that the speed is, if you like, it's uniform, it's constant speed, and the rate is a. So that's ds dt, traveling around. And that means that we can play around with the speed. And I just want to point out, so the standard thing, which you'll have to get used to, and this is a standard presentation. You'll see this everywhere in your physics classes and your other math classes. If you want to change the speed, so a new speed going around this would be if I set up the equations this way. now I'm tracing around the same circle, but the speed is going to turn out to be, if you figure it out, there'll be an extra factor of k, so it'll be a times k. That's what will work out to be the speed, provided k is positive and a is positive. So we're making these conventions that the constants that we're using are positive. All right? Now that's the first and most basic example, the one that comes up constantly. Now let me just make those comments about notation that I wanted to make. And we've been treating these square differentials here for a little while, and I just want to pay attention a little bit more carefully to these manipulations and what's allowed and what's not, and what's justified and what's not. So the basis for this was this approximate calculation that we had, that delta s squared was delta x squared plus delta y squared. This is how we justified the arc length formula before. And let me just show you that the formula that I have up here, this basic formula for arc length in the parametric form, follows just as the other one did. And now I'm going to do it slightly more rigorously. I do the division really in disguise before I take the limit of the infinitesimal. So all I'm really doing is I'm doing this, dividing through by this. And sorry, this is still approximately equal. So I'm not dividing by something that's 0 or infinitesimal. I'm dividing by something non-zero. And here I have delta x delta t squared plus delta y delta t, the quantity squared. And then in the limit, I have ds dt is equal to this square root of this guy, or if you like, the square of it. So. Okay, so it's legal to divide by something that's almost 0 and then take the limit as we go to 0. This is really what derivatives are all about, that we get a limit here as the denominator goes to 0, because the numerator is going to 0 too. All right, so that's the notation. And now I want to warn you maybe just a little bit about misuses, if you like, of the notation. We don't do absolutely everything this way. This expression that came up with the squares, you should never write it as this. Okay? This I've put it on the board, but very quickly. Hurry, hurry, hurry. Never. Okay? Don't do that. We use these square differentials, but we don't do it with these ratios here. But there was another place which is slightly confusing. It looks very similar, where we did use the square of the differential in a denominator. And I just want to point out to you that it's different. It's not the same. And it is OK. And that was this one. Whoops. This thing here. OK? This is a second derivative. It's something else. And it's got a dt squared in the denominator, so it looks rather similar. But what this represents is the quantity d over dt squared. And you can see the squares came in and squared the two expressions. And then there's also an x over here. All right? So that's legal. Those are notations that we do use, and we can even calculate this. It has a perfectly good meaning. It's the same as the derivative with respect to t of the derivative of x, which we already know was minus sine, a sine t, I guess. All right? Not this example, but the previous one, right, up here. So the derivative is this, and so I can differentiate a second time, and I get minus a cosine t. All right, so that's a perfectly legal operation. Everything in there makes sense. Just don't use that. There's another really unfortunate thing, right, which is that the 2 creeps in funny places, right, with signs, right? You have sine squared. It would be out here. It comes up here for some strange reason. You know, this is just because typographers are lazy, or somebody somewhere in the history of mathematical typography decided to let the 2 migrate, it would be like putting the 2 over here. It's, you know, there's inconsistency in mathematics, right? I mean, we're not perfect, and people just develop these notations. So we have to live with them. All right, the ones that people accept as conventions. All right, now the next example that I want to give you is just slightly different. It'll be a non-constant speed parameterization. Here, x is 2 sine t, and y is, say, cosine t. And let's keep track of what this one does. Now, this is a skill which I'm going to ask you about quite a bit, and it's one of several skills. You'll have to connect this with some kind of rectangular equation, an equation for x and y. And we'll be doing a certain amount of this today in another context. But right here, to see the pattern, we know that the relationship we're going to want to use is that sine squared plus cosine squared is equal to 1. So in fact, the right thing to do here is to take 1/4 of x squared plus y squared. And that's going to turn out to be sine squared t plus cosine squared t, which is 1. So here's the equation. Here's the rectangular equation for this parametric curve. And this describes an ellipse. Now, that's not the only information that we can get here. The other information that we can get is this qualitative information of where we start, where we're going, the direction. It starts out, I claim, at t equals 0. That's when t is equal to 0. This is 2 sine 0, cosine 0, right? 2 sine 0, cosine 0 is equal to the point 0, comma 1. So it starts up here at 0, comma 1. And then the next little place, so this is one thing that certainly you'll want to do. T equals pi over 2 is maybe the next easy point to plot. And that's going to be 2 sine pi over 2, cosine pi over 2. And that's just 2 comma 0. And so that's over here somewhere. This is 2 comma 0. And we know it travels along the ellipse, and we know the minor axis is 1 and the major axis is 2, so it's doing this. All right, so this is what happens at t equals 0. This is where we are at t equals pi over 2, and it continues all the way around, et cetera, to the rest of the ellipse. All right? This is the direction, right? So this one happens to be clockwise. All right, now let's keep track of its speed. Let's keep track of the speed and also the arc length. So the speed is the square root of the derivatives here. That would be 2 cosine t squared plus sine t squared. All right, and the arc length is what? Well, if we want to go all the way around, we need to know that that takes a total of 2 pi. So 0 to 2 pi. And then we have to integrate ds, which is this expression, or ds dt. So that's the square root of 4 cosine squared t plus sine squared t dt. All right, now, the bad news, if you like, is that this is not an elementary integral. In other words, no matter how long you try to figure out how to anti-differentiate this expression, no matter how many substitutions you try, you will fail. All right? That's the bad news. The good news is this is not an elementary interval. Integral, sorry. It's not an elementary integral, which means that this is the answer to a question, not something that you have to work on. So if somebody asks you for this arc length, you stop here. Okay, that's the answer. So it's actually better than it looks. All right, and we'll try to I mean, I don't expect you to know already what all of the integrals are that are impossible and which ones are hard and which ones are easy. So we'll try to coach you through when you face these things. It's not so easy to decide. I'll give you a few clues, but okay. So this is the arc length. Now I want to move on to the last thing that we did, last type of thing that we did last time, which is the surface area. And yeah, question.
I have a question. When you're drawing the ellipse there, do you not take into account what t is equal to, and you just draw the point over the axis?
The question, this is a good question. The question is, when you draw the ellipse, do you not take into account what t is? The answer is that this is in disguise. What's going on here is we have a trouble with plotting in the plane what's really happening. So in other words, we're kind of in trouble. So I wasn't, the point is that we have two functions of t, not one, x of t and y of t. So one thing that I could do if I plot things in the plane, in other words, the main point to make here is that we're not talking about the situation y is a function of x. We're out of that realm now. We're somewhere in a different part of the universe in our thought, and you should drop this point of view. All right? So this depiction is not y as a function of x. Well, you know, that's obvious because there are two values here as opposed to one. So we're in trouble with that. And we have this background parameter, and that's exactly why we're using it, this parameter t, so that we can depict the entire curve and deal with it as one thing. So since I can't really draw it, and since t is nowhere on the map, you should sort of imagine it as time, and there's some kind of trajectory which is traveling around. And then I just labeled a couple of the places. If somebody asked you to draw a picture of this, well, I'll tell you exactly where you need the picture in just 1 second. All right? It's going to come up right now in surface area. But otherwise, if nobody asks you to, you don't even have to put down t equals 0 and t equals pi over 2 here, because nobody demanded it of you. Yeah, another question. Yeah, so another very good question, which is exactly connected to this picture. So how is it that we're going to use the picture, and how is it we're going to use the notion of the t? The question was, why is this from t equals 0 to t equals 2 pi? That does use the t information on this diagram. The point is, we do know that t starts here. This is pi over 2. This is a pi. This is 3 pi over 2. And this is 2 pi. When you go all the way around once, it's going to come back to itself. These are periodic functions of period 2 pi. And they come back to themselves exactly at 2 pi. And so that's why we know in order to get around once, we need to go from 0 to 2 pi. And that's the same thing is going to come up with surface area right now. That's going to be the issue, is what range of t we're going to need when we compute the surface area. In a question, what you might be asked is, what's the rectangular equation for a parametric curve? So that would be 1/4 x squared plus y squared equals 1. And then you might be asked, plot it. Well, that would be a picture of the ellipse. Okay, those are types of questions that are legal questions. The question is, do I need to know any specific formulas? Any formulas that you know and remember will help you. They may be of limited use. I'm not going to ask you to memorize anything, except I guarantee you that the circle is going to come up, not the ellipse. The circle will come up everywhere in your life. So at least at MIT, your life at MIT. We're very round here. All right. Yeah, another question.
I'm just a tiny bit confused back to the basics, this is more of a question from yesterday, I guess, but when you have your original ds squared equals dx squared plus dy squared, and then you integrate that to get arc length,
Yes.
it's, how are you, the integral has dx's and dy's, so how are you just integrating with respect to dx and getting...
Okay, the question is, how are we just integrating with respect to x? So this is a question which goes back to last time. And what is it with arc length? I'm going to have to answer that question in connection with what we did today. So this is a subtle question, but I want you to realize this is actually an important conceptual step here. So shh, everybody listen. Right. If you're representing one-dimensional objects, which are curves maybe in space or in 2 dimensions, when you're keeping track of arc length, you're going to have an integral which is with respect to some variable. But that variable you get to pick. And we're launching now into this variety of choices of variables with respect to which you can represent something. Now, there are some disadvantages on the circle to representing things with respect to the variable x, because there are 2 points on the circle here. On the other hand, you actually can succeed with half the circle, so you can figure out the arc length that way, and then you can set it up as an integral dx. But you can also set it up as an integral with respect to any parameter you want. And the uniform parameter is perhaps the easiest one. This one is perhaps the easiest one. And so now the thing that's strange about this perspective, and I'm going to make this point later in the lecture as well, is that the letters x and y, you should, as I say, you should drop this notion that y is a function of x. This is what we're throwing away at this point. What we're thinking of is you can describe things in terms of any coordinate you want. You just have to say what each one is in terms of the others. And these x and y over here are where we are in the Cartesian coordinate system. They're not, and in this case, they're functions of some other variable. Some other variable. So they're each function. So the letters x and y just changed on you. They mean something different. X is no longer the variable, it's the function. All right? Well, you're going to have to get used to that. That's because we run out of letters, and we kind of want to use all of them the way we want. I'll say some more about that later. All right, so now I want to do this surface area example. I'm going to just take the surface area of the ellipsoid. The surface of the ellipsoid formed by revolving this previous example, which was example 2, around the y-axis. All right, so I want to set up that surface area integral here for you. Now, I remind you that the area element looks like this. If you're revolving around the y-axis, that means you're going around this way, and you have some curve. In this case, it's this piece of an ellipse. If you sweep it around, you're going to get what's called an ellipsoid. And there's a little chunk here that you're wrapping around. And the important thing you need besides this ds, this arc length piece over here, is the distance to the axis. So that's this horizontal distance here. I'll draw it in another color. And that horizontal distance now has a name. And this is, again, the virtue of this coordinate system. The t is something else. This has a name. This distance has a name. This distance is called x. And it even has a formula. Its formula is 2 sine t in terms of t. So the full formula for the integral here is, I have to take the circumference when I spin this thing around and this little arc length element. So I have here 2 pi times 2 sine t. That's the x variable here. And then I have here ds, which is kind of a mess. So unfortunately, I don't quite have room for it. Plan ahead. Square root of 4 cosine squared t plus sine squared t. Is that what it was, dt? All right, I guess I squeezed it in there. All right, so that was the arc length, which I recopied from this board above. Here, that was the ds piece. Sorry, it's this whole thing, including the dt. All right, that's the answer, except for one thing. What else do we need? We don't just need the integrand. This is half of setting up an integral. The other half of setting up an integral is the limits. We need specific limits here. Otherwise, we don't have a number that we can get out. So we now have to think about what the limits are. And maybe somebody can see. It has something to do with this diagram of the ellipse over here. Can somebody guess what it is? 0 to pi. Oh, that was quick. Wow. All right, that's it. Because we go from the top to the bottom, but we don't want to continue around. We don't want to go from 0 to 2 pi, because that would be duplicating what we're going to get when we spin around. All right? And we know that we start at 0. It's interesting because it descends. When you change variables to think of it in terms of the y variable, it's going the opposite way. But anyway, just one piece of this is what we want. All right? So that's the setup. And now I claim that this is actually a doable integral. However, it's long. I'm going to spare you. I'll just tell you how you would get started. You would use the substitution u is equal to cosine t, and then the du is going to be minus sine t dt. But then, unfortunately, there's a lot more. There's another trig substitution with some other multiple of the cosine and so forth. So it goes on and on. If you want to check it yourself, you can. All right, there's an inverse trig substitution which isn't compatible with this one. All right, but it can be done. Calculated. All right, in elementary terms. All right, yeah, another question.
Get this in the exam, do you want this?
So if you get this on an exam, I'm going to have to coach you through it. Either I'm going to have to tell you don't evaluate it, or you're going to have to work really hard, or here's the first step, and then the next step is keep on going, or something. I'll have to give you some cues because it's quite long. This is way too long for an exam, this particular one. Okay? It's not too long for a problem set. This is where I would leave you off if I were giving it to you on a problem set, just to give you an idea of the order of magnitude. Whereas one of the ones that I did yesterday, I wouldn't even give you on a problem set. It was so long. Okay? All right. So now our next job is to move on to polar coordinates. Now, polar coordinates involve the geometry of circles. As I said, we really love circles. Here, we're very round. Just as I love 0, the rest of the Institute loves circles. So we're going to do that right now. All right, what we're going to talk about now is polar coordinates. Which are set up in the following way. It's a way of describing the points in the plane. Here's a point in the plane, and here's what we think of as the usual xy axes. And now this point is going to be described by a different pair of coordinates, different pair of numbers, namely the distance to the origin, and the second parameter here, second number here, is this angle theta, which is the angle of ray from origin with the horizontal axis. So that's what it is in language, and you should put this in quotation marks because it's not a perfect match. All right? This is geometrically what you should always think of, but the technical details involve dealing directly with the formulas. The first formula is the formula for x, and this is the fundamental. These two are the fundamental ones. Namely, x is r cosine theta. The second formula is the formula for y, which is r sine theta. So these are the unambiguous definitions of polar coordinates. This is it. And this is the thing from which all other almost correct statements almost follow. But this is the one you should trust always. This is the unambiguous statement. All right, so let me give you an example of something that's close to being a good formula, and is certainly useful in its way. Namely, you can think of r as being the square root of x squared plus y squared. All right, that's easy enough to derive. It's the distance to the origin. That's pretty obvious. And the formula for theta, which you can also derive, which is that it's the inverse tangent of y divided by x. However, let me just warn you that these formulas are slightly ambiguous. So somewhat ambiguous. In other words, you can't just apply them blindly. You actually have to look at a picture in order to get them right. In particular, r could be plus or minus here. And when you take the inverse tangent, there's an ambiguity between it's the same as the inverse tangent of minus y over minus x. So these minus signs are a plague on your existence. And you're not going to get a completely unambiguous answer out of these formulas without paying attention to the diagram. On the other hand, the formula up in the box there always works. All right, so when people mean polar coordinates, they always mean that. And then they have conventions, which sometimes match things up with the formulas over on this next board. All right, let me give you various examples here first. But first, well, maybe first I should draw the two coordinate systems. So the coordinate system that we're used to is the rectangular coordinate system. And maybe I'll draw it in orange and green here. So these are the coordinate lines. Y equals 0, y equals 1, y equals 2. That's how the coordinate system works. And over here, we have the rest of the coordinate system. And this is the way we're thinking of x and y now. We're no longer thinking of y as a function of x and x as a function of y. We're thinking of x as a label of a place in the plane and y as a label of a place in the plane. So here we have x equals 0, x equals 1, x equals 2, etc. Here's x equals -1, so forth. All right, so that's what the rectangular coordinate system looks like. And now I should draw the other coordinate system that we have, which is this guy here. Well, close enough. And these guys here. Kind of this bullseye or target operation. And this one is, say, theta is equal to pi over 2. This is theta equals 0. This is theta equals negative pi over 4, for instance. So I've just labeled for you 3 of the rays on this diagram. It's kind of like a radar screen. And then in pink, this is maybe r equals 2, the radius 2. And inside is r equals 1. All right? So it's a different coordinate system for the plane. And again, the letter r represents measuring how far we are from the origin. The theta represents something about the angle, which ray we're on. And they're just two different variables, and this is a very different kind of coordinate system. Okay, so our main job is just to get used to this for now. You will be using this a lot in 1802. It's very useful in physics. And our job is just to get started with it. And so let's try a few examples here. Tons of examples. We'll start out very slow. If you have xy equals 1 comma minus 1, that's a point in the plane. I can draw that point. It's down here, right? This is -1 and this is 1. And here's my point, 1, -1. I can figure out what the representative is of this in polar coordinates. So in polar coordinates, there are actually a bunch of choices here. First of all, I'll tell you one choice. If I start with the angle horizontally, I wrap all the way around. That would be to this ray here. Let's do it in green again. All right? I labeled actually as -π/4, but another way of looking at it is that it's this angle here. So that would be r equals square root of 2, theta equals 7π/4. All right, so that's one possibility of the angle and the distance. I know the distance is square root of 2. That's not hard. Another way of looking at it is the way which was suggested when I labeled this with a negative angle, and that would be r equals square root of 2, theta equals -π/4. And these are both legal. These are perfectly legal representatives, and that's what I meant by saying that these representations over here are somewhat ambiguous. There's more than one answer to this question of what the polar representation is. A third possibility, which is even more dicey but also legal, is r equals -square root of 2, theta equals 3π/4. Now what that corresponds to doing is going around to here. We're pointing out 3/4 pi direction, but then going negative square root of 2 distance. We're going backwards. So we're landing in the same place. So this is also legal. Yeah?
The radiuses have to be positive because they represent a distance from the origin?
Right, the question is, don't the radiuses have to be positive because they represent a distance to the origin? The answer is, I lied to you here. All of these things that I said are wrong, except for this, which is the rule for what polar coordinates mean. Okay? So it's maybe plus or minus the distance is what it is always. Okay? Gotta be. Yeah, I try not to lie to you too much, but I do succeed. Now let's do a little bit more practice here. There are some easy examples, which I will run through very quickly. R equals A, we already know this is a circle. And the 3 theta equals a constant is a ray. However, this involves an implicit assumption, which I want to point out to you. So this is example 3. Theta is equal to a constant is a ray. But this implicitly assumes zero is less than or equal to r is less than infinity. If you really wanted to allow minus infinity less than r less than infinity in this example, you would get a line. It gives the whole line. All right? It gives everything behind. So you go out on some ray, you go backwards on that ray, and you get the whole line through the origin, both ways, if you allow r going to minus infinity as well. So the typical convention, so here are the typical conventions. And you will see people assume this without even telling you, so you need to watch out for it. The typical conventions are certainly this one, which is a nice thing to do pretty much all the time, although not all the time, most of the time. And then you might have theta ranging from minus pi to pi, so in other words, symmetric around 0. Or another very popular choice is this one, theta greater than or equal to 0 and strictly less than 2 pi. So these are the two typical ranges in which all of these variables are chosen. But not always. You'll find that it's not consistent. All right, let's do, as I said, our job is to get used to this. And I need to work up to some slightly more complicated examples, some of which I'll give you on next Tuesday. But let's do a few more. So example, I guess this is example 4. Example 4, I'm going to take y equals 1. That's awfully simple in rectangular coordinates, but interestingly, you might conceivably want to deal with it in polar coordinates. If you do, so here's how you make the translation. Now, this translation is not so terrible. What you do is you plug in y equals r sine theta. That's all you have to do. And so that's going to be equal to 1, and that's going to give us our polar equation. The polar equation is r equals 1 over sine theta. There it is. And let's draw a picture of it. So here's a picture of the line y equals 1. And now we see that if we take our rays going out from here, they collide with the line at various lengths. So if you take an angle theta here, there will be a distance r corresponding to that, and you'll hit this in exactly one spot. For each theta, you'll have a different radius. And it's a variable radius. It's given by this formula here. And so to trace this line out, you actually have to realize that there's one more thing involved, which is the possible range of theta. Again, when you're doing integrations, you're going to need to know those limits of integration, so you're going to need to know this. The range here goes from theta equals 0, that's sort of when it's out at infinity, that's when the denominator is 0 here, and it goes all the way to pi, swing around just 1/2 turn. So the range here is 0 less than theta less than pi. Yeah, question?
Is it typical to express r as a function of theta or vice versa, or it doesn't matter?
The question is it typical to express r as a function of theta or vice versa, or does it matter? The answer is that for the purposes of this course, we're almost always going to be writing things in this form. R is a function of theta. And you can do whatever you want. This turns out to be what we'll be doing in this course exclusively. It's as you'll see when we get to other examples, it's the traditional sort of thing to do when you're thinking about observing a planet or something like that. You're observing you see the angle, and then you see you guess how far away it is. So but it's not necessary. The formulas are often easier this way for the examples that we have, because it's usually a trig function of theta, whereas the other way it would be an inverse trig function. So it's an uglier expression. All right? As you can see, the real reason is that we choose the thing that's easier to deal with. All right. So now let me give you a slightly more complicated example of the same type where we use a shortcut. This is a standard example, and it comes up a lot. And so this is an off-center circle. A circle is really easy to describe, but not necessarily if the center is on the is on the rim of the circle. All right, so that's a different problem. Now let's do this with a circle of radius a. So this is the point a comma 0, and this is 2a comma 0. And actually, if you know these two numbers, you'll be able to remember the result of this calculation, which you'll do about 5 or 6 times, and then finally you'll memorize it during 1802 when you will need it a lot. So this is a standard calculation here. So the starting place is the rectangular equation, and we're going to pass to the polar representation. The rectangular representation is x minus a squared plus y squared is equal to a squared. So this is a circle centered at a comma 0 of radius a. And now, if you like, the slow way of doing this would be to plug in x equals r cosine theta, y equals r sine theta, the way I did in this first step. And that works perfectly well. But I'm going to do it more quickly than that, because I can sort of see in advance how it's going to work. I'm just going to expand this out. All right? And now I see the a squareds cancel. And not only that, but x squared plus y squared is r squared. So this becomes r squared, that's x squared plus y squared, minus 2ax is equal to 0. All right? The r came from the fact that r squared is equal to x squared plus y squared. All right, so I'm doing this the rapid way. You can do it by plugging in, as I said, r equals. So now that I've simplified it, I am going to use that procedure. I'm going to plug in. So here I have r squared minus 2a r cosine theta equals 0. I just plugged in for x. As I said, I could have done that at the beginning. I just simplified first. And now, this is the same thing as r squared is equal to 2a r cosine theta. And we're almost done. There's a boring part of this equation, which is r equals 0. And then there's, if I divide by r, there's the interesting part of the equation, which is this. So this is or r equals 0, which is already included in that equation anyway. All right, so I'm allowed to divide by r because in the case r equals 0, this is represented anyway. Question?
How does the case r equals 0 represent that circle?
R equals 0 is just one case. That is, it's the union of these two. It's both. Both are possible. So r equals 0 is one point on it, and this is all of it. Okay, so we can just ignore this. All right, so now I want to say one more important thing. You need to understand the range of this. So wait a second, and we're going to figure out the range here. The range is very important, because otherwise you'll never be able to integrate using this representation here. So this is the representation, but notice when theta is equal to 0, we're out here at 2a. That's consistent, and that's actually how you remember this factor 2a here, is if you remember this picture and where you land when theta is equal to 0. Right? So that's the theta equals 0 part. But now as I tip up like this, you see that when we get to vertical, we're done with the circle. It's gotten shorter and shorter and shorter, and at theta equals pi over 2, we're down at 0, because that's cosine of pi over 2 is 0. So it swings up like this, and it gets up to pi over 2. Similarly, we swing down like this, and then we're done. So the range is minus pi over 2 is less than theta is less than pi over 2. Or if you want to throw in the r equals 0 case, you can throw in this. This is repeating, if you like, at the ends. All right, so this is the range of this circle. And let's see. Next time, we'll figure out area in polar coordinates.